Next, we'll discuss both bump mapping and normal mapping, two methods for simulating fine details on the surface of an object without the need for supporting geometry. Now, we know from our lecture on materials that surface shading is calculated by considering the surface normal at a particular point on the object, right? That'll be the vector normal to the polygon itself, as well as an incoming light vector. Bump mapping and normal mapping exploit the fact that surface shading can radically be altered simply by changing the surface normal using a bitmap texture. So just to be clear here, what we're doing is we're actually, we will not be using the true surface normal of the polygon itself, but we'll actually be specifying a different surface normal, right? And if we think about it, it'll make sense that this is really all that's necessary to just simulate surface detail. And right, using a bitmap image and just using pixel values to specify different normal vectors along the original surface, we can start creating some really fine detail just using an image texture. And start faking some really nice surface details, which otherwise would require probably on the order of hundreds of thousands, if not millions of polygons to simulate. All right, so just to be clear here, with both bump mapping and we're going to see with normal mapping, all we're doing here is modifying the surface normals used in the shading calculations, as they interact with the incoming light vectors. That's all we're modifying here, using an image texture. All right, so because what we're doing is, offering new surface normals to be used in the shading calculations, yes, we're able to simulate surface detail. However, the profile of an object will remain the same. It will remain described only by the geometry itself, and either a bump map or a normal map, which we'll look at in just 1 second, will not alter the profile of the object. Right. So let's say we're taking a side view of some cube or something like that, maybe using a bump or a normal map. We're specifying, different surface normals to use at various surface points. But keep in mind here, this has nothing to do with the geometry itself. All that this is going to accomplish is, as we calculate the shading here, by taking into account incoming light vectors, we're going to get lots of nice surface detail here. However, the profile of the object, the physical profile, if you will, is going to remain unchanged, right? Again, if this is just a cube and we looked at it from a side view, well, there's no additional geometry here. It is still going to be a cube. So we do have to be careful if we're trying to simulate really coarse details which in normal circumstances should change the profile of the object, things that really protrude far off the surface, right? If we're trying to simulate like some sort of a really bumpy surface like this, it might look okay if we had our camera up here and we were just observing the this surface of the object. But if we were looking again from our point of view, this side view, we'd expect to see profile changes. We'd expect to see this on the side view of the object. Not possible with a bump or normal mapping. Okay, so that's important to keep in mind. Additionally, details that we simulate using these modified surface normals, it's not going to be possible to produce self-shadowing with these, right? again, if these were physical surface details created using geometry, then if we had some sort of incoming light vector, then well, yeah, we'd be able to see shadows cast by these surface details. Of course, this is not going to happen with bump or normal maps, so that is worth taking into account. All right, so the simplest way of faking non-profile changing details is to use what we call bump mapping. So with bump mapping, we use a grayscale image and treat it as a height map. All right, so now we briefly talked about height maps earlier in the course, and we talked about how these could be used to maybe displace geometry. We'll actually talk about something called displacement maps a bit later on here. But for the time being, we'll just discuss this grayscale image as a height map that is used in a very particular way to actually produce modified surface normals on the surface of the object, right? So darker values such as this, it's about 50% gray or so. This will give a lower height value, right? It's actually a number closer to 0. So this gray here is going to give a lower height value. Let's just say this gives us a lower height value, and this brighter gray color is going to give us a higher height value. Just because the number is closer to 1, the number being used to store these lighter gray colors. And so what this is going to result in when we use this grayscale bump map on a piece of geometry is it's going to produce something like this. All right, so let's say that this blue line is, again, kind of a side view of a polygon. Let's say we had so this kind of dark gray color, maybe that produces a height value, something like this, some uniform height value, anywhere we get this gray color mapped onto the polygon itself. But then when we come across this brighter gray color, well, of course, that's a number closer to 1, so we're actually going to get a higher height value here, right? So, and actually, let's actually bring in kind of this transition, right? It's kind of a soft shape here. There's a bit of a transition from the dark gray to the light gray. Let's get some of these intermediate values here and just show that transition taking place. Right, so I'm just sampling a few of these transition values. Again, this isn't like perfectly accurate, but just to get the general idea across, right? We would be able to see these different height values from a side perspective. There we go. So now we're at that full brighter gray there, and then if we're kind of simulating what this bump map shape is going to look like, then well, that lighter gray value is going to continue for a while before at this kind of constant height before transitioning back to the darker gray. All right. And so what this actually produces is a way of simulating different normal vectors on the surface of the object, right? We know the true normal of this polygon is a perpendicular vector like this, but let's connect each of these different height values that we just created here. So I'm just going to go through here and connect each one. We're going to notice something very interesting about this. All right, so each of these areas that we've connected together here can produce a different normal vector. All right, so this is how bump mapping produces modified surface normals to use with that shading equation, right? When we take into account incoming light vectors, well, we actually take into account how those incoming light vectors interact with the modified surface normals, right? So instead of, let's say we have a light source here, and instead of just for any point on the surface of this polygon, instead of just calculating the shading, let's only talk about diffuse shading in this case, right? Instead of only considering a constant diffuse shading value corresponding to this roughly 45-degree angle that the incoming light vector makes with the polygon normal, what we can actually do here is calculate, well, we're going to get, basically that 45-degree angle for these points up here at the top of this kind of light gray area on the bump map. But then on this transition here, well, there's an abrupt change. Take a look at this, right? This is an angle far closer to 90 degrees. So this surface, because it's angled away from the light source, it's going to be a lot darker, isn't it? Right? Take a look at these ones. Again, it's a vector. Again, it's an angle pretty close to 90 degrees. This area is angled quite a ways away from the light source. This one's a bit closer, right? So this surface point right here, if it is observed by the camera during rendering, it'll be a bit brighter. And then finally, we'll transition back to something around that original 45-degree angle. All right, so that is the general idea of how bump mapping works. And just to demonstrate the effects of bump mapping, I've taken this image, again, just the lighter gray bars on the darker gray background, and assigned that as a bump map onto this plane, and just rendered that with just a simple area light off to the side here. And we can see the effects here. We can see those details appearing to be raised off the surface of the object. However, again, just to demonstrate the fact that the profile of the object has not changed, right? If we angle our camera such that it's almost parallel with the plane itself, we're going to see that nothing has been raised off the surface of the plane. It is still a flat object. The effect we're simulating here has only to do with the fact that the surface normals have been changed when rendering each of these pixels of the final image. The surface normals of the observed surface point on the object have actually been modified for that shading calculation that we're doing. Now, normal mapping provides another method for altering surface normals during the shading calculation, and this actually ends up being the method most commonly used to do this, chosen over bump mapping, just because the process is in fact a little bit more efficient. All right, and it all comes down to how normal mapping actually modifies surface normals. Let's take a look at how this works. So again, if you've ever done some texture work before in 3D, you've probably come across normal maps, and you may have wondered, why are they this strange purpley bluish color, with some other weird colors showing up, representing the shapes of these details that we're trying to simulate. What on earth is going on with this strange coloring? The reason these particular pixel colors are used to represent surface details is because what we're doing is actually storing an entire three-dimensional vector in a single pixel value. So how can this be? How can we store an entire three-dimensional vector using only the data allocated to a single pixel in a color bitmap image? Well, fortunately, an RGB image has 3 integer values available to us to store data for each pixel, right? So instead of storing color information in our red, green, and blue channels, we're actually going to store the X, Y, and Z coordinates of a surface normal. All right, so red is going to be for the X component of this new vector, green is for Y, blue is for Z, and well, we can just go ahead and encode an entire surface normal in a single pixel value, right? Pretty brilliant, isn't it? So in contrast to bump mapping, where we use a height map to kind of modify surface normals, what we're actually doing here is storing entire surface normals, and we're replacing the surface normals of our geometry using the vectors stored in the pixels that are mapped onto certain surface points, right? Let's just draw that out because, again, that's the big sentence that might be a little bit confusing. So again, we've already discussed UV mapping and how the image texture itself, we have a remapping of 2D coordinates onto some part of of a polygon itself. And so, right, so let's say that this UV coordinate for this pixel right here has been remapped onto this location on the polygon itself. Well, that means that this, I'm just going to color select this value, this color value right here, and just draw that pixel in there, right? So if this surface point is observed during rendering, if this surface point is observed, I'll just draw a circle around that, then we're just going to go and find the color information associated with that surface point on the polygon. We're going to find that it is this blue color right here, and we're going to be able to look at the RGB color channel values for that kind of bluish color and get a surface normal from that. All right, so now let's just take a look at how these vectors are encoded as pixel values. Well, in order to define any normal vector, we're going to need to be able to encode the values -1 to 1 for the X, Y, and Z axes respectively, right? If we can store values from -1 to 1, then we can create a unit vector representing any surface normal we want. And so the way we do that is just by mapping the values -1 to 1 to the range 0 to 255, right? At least for an 8-bit color image, 0 to 255, that is the integer range available to us for each color channel, right? We only have 8 bits of information to use to store color values. So we just remap the range -1 to 1 to the range 0 to 255. So, well, have you ever wondered why the default color or the default non-detailed color on a normal map is this strange purpley blue color, right? Seems kind of arbitrary. So why is it precisely that? Well, it's because it's because of the normal vector that this color encodes. So let's actually take a look at that, right? Let's color select. I'm just going to use the eyedropper in Photoshop here and just color select that bluish color there. Going to take a look at the RGB components of that color, and we can see that we have red being equal to 128, G 128, and B 255. So let's just write those down. So red is 128, green is 128, and blue is 255. And just taking a look at the values, 128 is directly in the middle of the range 0 to 255, right? It's 256 divided by 2, right? So smack dab in the middle of this integer range for our color values, for red and green at least, would give us exactly in the middle of the range of our 3D coordinate values, right? So that would give us a 0, right? So let's just convert this back to XYZ coordinates here, right? So for the red channel, we would get a 0. For the green channel, we would get a 0 as well, right? That is what 128 remapped to the range -1 to 1 gives us. And then the value 255, well, that is at the far, I guess, the right-hand side of the range of color integer values, which corresponds to, well, the far right-hand side of the remapped -1 to 1 range, right? So the blue value of 255 will give us a +1. So it turns out that this default bluish color, if you take a look at the XYZ coordinates that encodes, it actually encodes a normal vector pointing up directly along the z-axis. Right, so if we looked at this, if we looked at a polygon from a side view, right, that would be x equals 0, y equals 0, and then z equals +1. Right, so that is why this default color is kind of this strange blue. And then all of these other colors here, right, we could just color select these values, like this one right up here. Take a look at the RGB components and see that, well, this will turn into a 0 on the x-axis. This is 226, so it's fairly close to 255. This is a large positive number on the y-axis, and 209, a slightly smaller positive number on the z-axis, right? So we could actually just remap these values back to the -1 to 1 range to find out the precise XYZ coordinates that each pixel value encodes. And then, for the rest of it, the rest of normal mapping behaves the same way with bump mapping, right? We're just using these modified normals that are produced to just alter the shading calculations as they're performed for each surface point on various polygons. And so again, in Maya, just to demonstrate the effects of normal mapping, I've taken this normal map just with this surface detail kind of raised off the surface of the polygon, and just place that on this plane again. And by rendering this out, we can see that we are getting that effect. Now, this is actually a fairly distinct detail. It's actually raised a fair bit off the surface of the object. So, maybe not the best choice of detail to simulate using normal mapping. It's pretty easy to tell that this is a normal map. Just angling our camera to the side here like we did before, we can see that, this starts to look really bad. This is pretty much an example of what not to do. You do not want to try and simulate details that protrude a large distance off the surface of a polygon. Otherwise, it's going to start to look really dumb and flat and non-realistic. However, perhaps perhaps from enough of a distance, and if the camera was head on, facing the polygon, at a more or less perpendicular angle, this could be, this could be appropriate, right? That's starting to look not too bad there. All right, now before we leave this section, we'll actually talk a bit about displacement mapping, which is a very interesting way of using a texture, like these textures we've just been looking at. I have this bump map up yet again, just so we can take a look at it. But using textures to actually displace actual geometry, right? Not just try and fake the details on the surface of the object in a way which does not modify the geometry of the object and the profile of the object, but in a way that actually displaces geometry itself. So this is where displacement mapping comes in. Yes, indeed, this is possible. And while there are perhaps fewer use cases for displacement mapping than something like normal mapping, it is still very possible and quite useful in certain circumstances. So with displacement mapping, a height map, similar to the one that we used here with bump mapping, can be used. However, in this case, basically a relatively low resolution mesh will actually be subdivided at render time, and the newly available dense geometry will actually be physically displaced when the image is rendered. So let's get rid of this height map, and let's go ahead and render this plane. I already have it up here, but let's go ahead and render this again, this time using displacement. And so what we can see here is, these details being raised off the surface of the object, they are actually, these are actually formed of physical geometry. We can zoom in nice and close here, angle our camera, again, almost parallel to the plane itself, almost on the surface of the plane itself, and see that the profile of the object has been changed. This is actual geometry that has been created here, and the results can actually be quite interesting, and we can create some really nice details using this. And keep in mind that, again, we have not actually changed the source geometry here. It is still just a plane, just a single quad polygon here. This is where the true power of displacement mapping really comes in. So the reason this is done using comparatively low resolution geometry and a texture instead of, subdividing the geometry and just modeling in the details by hand and storing those modified vertices, this is because of a few reasons. So first of all, we can keep our file sizes fairly low by having the geometric detail here, which can easily be creating detail at the scale of millions of polygons. We can have this all generated at render time using only bitmap information stored in an image, which is trivial in size compared to the disk space required to actually store the millions of polygons that we're simulating. The other reason we might want to use displacement maps to achieve surface details like this is because render time displacement is actually a task that can be performed directly on the GPU, meaning that a massive multi-million polygon model does not have to be passed to the GPU from memory, which is a fairly slow process, right? So again, just to be clear here, we're passing, in this case, we're passing 4 vertices, one quad polygon to the GPU. The GPU is then subdividing it at render time and doing this displacement based on the height map, all in one place, right? So comparatively, if we were to literally have this polygon subdivided to the point of having, it would probably be on the order of a few tens of thousands, if not hundreds of thousands of polygons for this single polygon. That would probably not only slow the Maya viewport down to a crawl, but it would also be very time consuming to actually pass all of that information to the GPU in order to render it. So for certain use cases, displacement mapping can offer a fantastic solution to achieving highly detailed objects, with, of course, one major benefit being the fact that the actual geometry is displaced, right? We've just seen this, that the object's profile itself is actually modified, and, therefore self-shadowing is possible, and overall it is going to look quite convincing. However, you do need a height map. You need to generate a height map that accurately simulates the details that you want to create, right? So if you're able to do that using a height map, then displacement mapping can be a great solution for creating those sorts of details for your models. And before we finish off this section, let's just take a look at light maps. So light maps offer a way to simulate high-quality lighting in an application where such lighting would be difficult or impossible to otherwise achieve. Right? There's a theme in the topics we've looked at in the last few sections here, and that theme is simulating details and effects that would otherwise be more difficult or computationally costly to achieve. Right, so lighting is another opportunity to take advantage of some of these methods, and so yeah, let's take a look at this idea of baking lighting information in a scene to again a texture. So, for example, in 3D games, right, lighting has historically been baked offline to textures, right, such that at runtime, the objects in the scene can have their colors and textures modified by this baked light map, displaying anything from shadows cast by objects to beautiful global illumination effects, easily in real time. Effects that, again, at least from a historical standpoint, have been very difficult to achieve in real time. Right? Of course, this is changing with newer technology available to game developers now, with better and better hardware, it seems, coming out every couple years. But nevertheless, the idea of light maps still stands, right? So let's just quickly render out this example scene here. Right, I already have it up, and it just shows a directional light source shining on this cube and this plane. And we can see that the cube is casting a shadow onto the plane. So we can bake all of this lighting information to actual textures and just map those textures onto this very same geometry. And I mean, actually, in this case, we can render the whole scene without any lights at all. And so I'll just reveal this other version here. And so we can see actually a slightly different scenario. In this case, the light source was directly on top of this cube. And we could see that the shadow was being cast directly underneath the cube itself. But there is no light involved in creating this shadow that appears as though it's being cast by the cube. Right, let me go ahead and pull up the texture being used to create this effect. Right, this light map right here. This is just another bitmap texture, just like any old image texture. And what it does is it contains this lighting information. Right, this area right here. This is the shadow originally cast by some light source. However, because this information is now baked to an image, well, we don't even need the light anymore, right? So that is the general idea of light maps, baking lighting and shadowing information to image textures, and then just displaying all of that information just as image textures on the objects themselves. Now, the only downside to baking and using light maps is that, the real-time objects and light sources can't be moved after we bake lighting, right? Again, this isn't going to make a lot of sense if we try and move this cube around. Well, the shadow baked onto the plane, well, we'd expect that to move with the cube, right? However, because it is baked lighting information, it is not going to move. So that is a major downside of working with light maps. So in practice, and the way this would typically be used in a game would be you'd probably have most, if not all, of the lighting information and shadowing baked in for environment assets that don't end up moving during the runtime, and then for any object that is going to move, such as a player character or something like that, you'd use a real-time light for that, casting a real-time shadow. Definitely less computationally expensive than having to cast static shadows in every frame for all of these immovable environment objects. So yeah, that's how the lighting scenario in a real-time environment can easily be optimized, right? By baking static lighting to just to image textures, and then still using a real-time light source for anything that is going to move at runtime.